Hi everyone. In the last session, we have seen parts of electric drive. That is one of the parts of electric drive, power modulator. We focused. In today's session, we'll see the choice and status of electric drives. So, choice of electric drives. The choice of electric drives depends on the following factors: steady state operation requirements like nature of the speed torque characteristics, what type of speed torque characteristics do the load required, and speed regulation, speed range, in what range we need to operate the drive, efficiency, duty cycle, quadrant of operation. Among the four quadrant of operation, whether we need only motoring, braking, or reverse motoring, reverse braking also, like that quadrant of operation, speed fluctuations, and if any other ratings. So depends on the steady state operation requirements, we need to choose the proper electric drive. And other type transient operation requirements like value of acceleration, deceleration, starting, braking, and speed reversal. So all these are transient operations. So during acceleration, deceleration, how the speed need to be pick up, or speed reversal, how much time does it need require. So all these things matter while choosing the electric drive. Requirements related to the source, type of sources and its capacity, magnitude of voltage fluctuations, power factor, harmonics, and their effect on loads, and ability to accept the regenerated power. So all these factors are matter whether the drive need to regenerate some power, or it can simply wasted that power by connecting some rheostat. So by or type of sources like voltage levels, whether it is small or low power or high power requirements. Based on that, we need to choose the electric drive. Whether the power factor should be good or medium, fluctuations in the voltage, few sensitive applications are there, right? So for that, we do not choose that few type of drives. So capital and running cost, maintenance needs, and the life of the equipment or drive. Next one is space and weight restrictions. If you see the aerospace applications or aircraft applications, there the weight is matter, space is matter. So there we need to choose one type of drive which will give the space and weight less. Environment and location. In few drives, explosive environments will be there, radioactive environments will be there where few drives will give some sparkings that we can avoid. And the location, on which location you are keeping the electric drive, like it is on the top of the turbine, wind tower, or it is in the submerged. So that location also matters while choosing the electric drive. And the reliability, based on the reliability, we can choose one of the drive. Squirrel cage induction motor, it is more reliable. Even though it has some drawbacks, it is more reliable. If it requires, we can choose the type of drive if that application requires more reliability. Next one is status of DC and AC drives. So the status of AC and DC drives, generally it is in the textbooks. It was mentioned long back. Now many advances have come, but that time what was the status of AC and DC drives means it was predicted that the induction motor drives will replace the DC drives in variable speed applications. However, the following hurdles forbidden for the prediction to come true. Nowadays, many induction drives have come, but earlier there was a prediction. So, what are the hurdles to hurdles? Hurdles means, although the squirrel cage induction motor was cheaper than the DC motor, the converter and control circuit of an induction motor drives was very expensive compared to those of a DC drives. Therefore, the total cost of the induction motor drive was significantly higher than that of the DC drive. In DC drives, only DC drive and associated control circuit. If you compare that cost with the AC drive, squirrel cage induction motor with control circuit, associated control circuit will be more costlier than the DC drives, because even though the squirrel cage induction motor is cheaper, the control circuit becomes costlier. Because of that, the overall cost of that particular AC drive is more or was more. While the technology of the DC drives was well established, than that of the AC was new. The time the DC drives were well established than the AC drives. AC drives were not reliable as the DC drives. Compared to the DC drives, AC drives are not that much reliable. Development in linear and digital ICs and VLSI were helpful in improving the performance and reliability of the AC drives. But then these developments also fed to similar improvements in DC drives. That means developments like control circuit cost can be the development to reduce the cost of the control circuit, makes the overall cost of the AC drives cheaper than the DC drives. But the same development will be there in the DC control circuits also. That makes relatively lesser cost than the AC drive. Improvements in thyristor capabilities like GTO, gate turn-off thyristor, and IGBTs in 1980s, and developments in VLSI and microprocessor have resulted into reduction in cost and simple controllers and improvements in performance and reliability of AC drives. So all these developments, because of the power semiconductor devices, the control circuit cost becomes lesser. So because of that, the total AC drive cost have come to less, and the reliability also improved. Induction motors are preferred in low and medium power applications generally, and synchronous motors used in medium and very high power applications. And permanent magnet synchronous motor and brushless DC motor replacing the DC servo motors for fractional HP range. So these BLDC motors have come. If you see present days BLDC motor in almost all the applications we are using by replacing the DC servo motors for the low power applications. As the trend exists, applications of AC drives will continue to grow. However, DC drives will also continue to be used for quite some time. So that's what it is happening, even though we can find the DC drives in most of the applications as of now also. Even though the AC drives have developed, or the cost and reliability of the AC drives have increased, even though the DC drives is usage of DC drives also continuing. The best example is traction. In traction, we use the DC drives. So the DC drives nowadays, that DC drives are replacing with the AC drives, but that technology we are developing, and although it was well established, here we are slowly adopting, or we are changing or transiting to the AC drives in the traction also. Really we'll use a DC series motor in the traction. So that need to be slowly DC series motor, thyristor circuits. So that kind of drive nowadays we are using in the traction. So in few traction applications, in few locomotives, now we are using the induction drives also, that is AC drives. So DC drives and their performance. So DC drives are widely used in applications requiring in adjustable speed, good speed regulation, and frequent starting, braking, and speed reversal. The applications are like rolling mills, paper mills, mine vendors, hoist, traction, printing press, textile mills, and cranes are the few applications of the DC drives. If you see the DC motor, generally DC drives will use a DC motor. So we should know just to brush up that DC motor concepts. So DC motors and their performance. You see, we will see this briefly. So first one is type of DC motors. There are few types of DC motors. One is separately excited DC motor, shunt motor, series motor, compound motors. If you see the figure A, separately excited DC motor, where the armature and field both are separately connected with the DC supply. That is called the separately excited DC motor. Your armature is connected with V and your field is connected with the VF. Both are connected separately with the different levels of DC voltage. So that is called the separately excited DC motor. And whereas in shunt type motors, your armature or your field is connected across the armature and that is connected with the supply. Your field is connected across the armature. And coming to the series type of motors, your field is connected, the inductor type coil is nothing but field. Field is connected in series with the armature and to the supply. That is called the series motors in C. And D, cumulatively compound motor. A part of the field winding is connected in series with the armature. That combination again it is connected in parallel with the field winding. So that is called the cumulative compound to get the different type of characteristics. So few basic equations we will see, fundamental equations like steady state equivalent performance. So basic equations applicable to all type of DC motors are the generated back EMF. If you see that the basic diagram of the DC motor is shown in the figure. Your supply is connected with the armature resistance and motor. That is nothing but armature of the motor. The generated back EMF E is nothing but E is equal to Ke into pi omega m. E is directly proportional to pi omega m. So by removing the proportional, E is equal to some constant Ke, that is motor constant. K is called motor constant, Ke into pi omega m. So that is a generated back EMF. Whereas if you apply the KVL to that figure, then V is equal to E plus Ia into Ra. Ia is nothing but armature resistance, Ia is nothing but armature current, Ra is nothing but armature resistance. Drop across the armature resistance is Ia into Ra. E is the back EMF, V is the supply voltage. V is equal to E plus IaRa. So this E is equal to Ke into pi omega m. If it is series motor means we can replace that pi with the If value. If it is shunt motor means pi is another constant. So again if you see the V equation, supply voltage V is equal to E is plus Ia into Ra. And from this equation again we can rewrite that equation, E is equal to V minus IaRa. E, back EMF E is equal to V minus IA RA. Just you E right side, you can keep E, and E is equal to V minus IA RA. Now the torque equation T is equal to Ke into pi Ia. Torque T is directly proportional to pi Ia, that can be replaced with the T is equal to Ke into pi Ia. If it is series motor means pi is directly proportional to IF. If it is shunt means pi is constant. So in these three equations are very important. In almost throughout the DC drives will use these three equations. Here pi is nothing but flux per pole in Webers, Ia is nothing but armature current in amperes, Ra is the armature resistance in ohms, omega m is equal to speed of the armature in radians per second, torque T is nothing but torque developed by the motor in Newton meter, and Ke is equal to motor constant. So as I told you that V is equal to E plus Ia Ra can be rewritten as back EMF E is equal to V minus Ia Ra. Back EMF E is equal to V minus Ia Ra. Here if you see, E can be replaced with again Ke into pi omega m. E is equal to V minus Ia Ra. You assume that E is equal to V minus Ia Ra. E can be replaced with omega Ke pi omega m, right? By keeping that omega m on the left side, if you take Ke pi on the other side, then V by Ke pi minus Ia Ra by Ke pi. So here I can replace that Ia, armature current, by using this torque equation. Torque T is equal to Ke into pi Ia, right? From there Ia is equal to T by Ke pi. So in the first equation, omega m is equal to V by Ke pi minus Ra Ia by Ke pi. There Ia can be replaced by T by Ke pi. So that I'll get V by Ke pi minus Ra into T by Ke pi whole square, because Ia is equal to T by Ke pi. So these are the general equations. If you go shunt and separately excited motors, for shunt and separately excited DC motors, the field current is constant. The flux can be assumed to be constant, hence the flux can be assumed to be constant. So Ke into pi is equal to another constant K. Let us assume another constant as K. Now K into pi is equal to K. So torque, earlier the basic or fundamental equation is nothing but T is equal to Ke pi into Ia. Now for the shunt and separately excited DC motors, your K into pi can be replaced with another constant K. Hence your T is equal to Kia, and E is equal to Ke pi into omega m, right? Ke pi can be replaced with the K. Hence E is equal to K into omega m. From these two equations, E is equal to Ke pi omega m. So here Ke pi can be replaced with K, and T is equal to Ke pi Ia. Here K into pi can be replaced with another K. That's what here I have written. Equal to Kia, E is equal to K omega m. Now again E is equal to V minus Ia Ra. E can be replaced with K into omega m. By keeping that omega m alone on the left side, omega m is equal to V by K minus Ia Ra by K. Ia can be replaced with the T by K, so that your equation will become V by K minus Ra by K square into T, simply by replacing that Ia with the T by K. And for series motor, here the flux is a function of the armature current. It is not constant, armature current, function of the armature current. In unsaturated region of the magnetization characteristics, flux can be assumed to be proportional to the armature current in series motor. Thus, your flux is directly proportional to armature current Ia means that proportionality can be removed by keeping some constant, that is pi is equal to Kf into Ia. Again, this pi is equal to Kf into Ia. Substitute in the fundamental equation. The fundamental equation is nothing but T is equal to Ke into pi Ia, right? Ke pi Ia. Pi can be replaced with Kf into Ia. So hence the equation T will become Ke Kf into Ia square. Ia into Ia. That will become Ia square. So again, by substituting the same omega m equation, that is nothing but E is equal to V minus Ia Ra. E can be replaced with Ke into Kf into Ia omega m, right? So by substituting in that omega m equation, just to remember that omega m is nothing but V minus Ia Ra by K, if it is fundamental equation. Again, if you are replacing pi with Kf into Ia, the corresponding Ke into Kf, all constants also will come along with the omega m. So that's what we got here. Like the shunt motor, here we got the omega m equation as V by square root of Ke Kf into 1 by root T minus Ra by Ke Kf. Just a simple you need to do one more step, then you will get that. Performance curves of DC motors. If you see the speed torque characteristics, in the speed torque characteristics for separately excited motor, we will get the drooping characteristics are almost constant characteristics by neglecting the armature resistance drop. And for series motor, initially it is high torque and torque will be less for the then for the compound motor, the characteristics of the dotted line, it is mentioned with the headings. This is for series motor, separately excited motor, and like this you will get the series motor, and this is for compound motor. These characteristics we have drawn by keeping the rated voltage and fulfilled. And torque versus armature current characteristics are shown in the figure B here. So for separately excited motor, torque is directly proportional to armature current, hence it is like this. For compound motor, for series motor, torque is directly proportional to armature current. Okay. That's why you will get the characteristics like this. In between, you will get the compound characteristics. The usual drop of the speed from the no load to full load is around 5% in medium sized motors. There is a 5% drop generally we can notice when it is from no load to full load in medium sized motors. So this is all about the status and the choices of DC drives and DC motor performance, or DC drives and DC motor performance. Thank you all.